the topic that is called psi classes. So psi classes, so a bit of history. First, psi classes appeared when the people wanted topological gravity. Namely, they appear as observables on M, no, not M. And here we have Deligne-Mumford compactification. Well, the first thing that people started to do was computation. Of psi classes oh, GM in genus 0. So let me review a bit of this computation. Because later it turned on that they have much more interesting story. But they appeared like this. So consider sphere with n marked points. How to define this class? We need to start with the one with the omega that should be one form, say at Z1. And this one form at Z1 should depend on Z2, etc., Zn. And we may look for such configurations where it has zeros or poles. So one form is a section of T star. So we would take its poles. Okay. So we need to include both zeros and poles. Okay? So we would concentrate, as we will consider zeros, say with sign +1, and poles with sign -1. Okay, so to do it, let us consider an example. let us take, say, dz1. So it's not a nice differential because it has poles at infinity in coordinate z1. Actually, if you write coordinate at infinity z1 tilde equals 1 to z1, then dz1 is dz1 tilde, z1 tilde square with a minus. So it's not what we would like to get, because this infinity is not internally important piece on the moduli space. It doesn't correspond to anything special. So it means that this is not the differential that we would like to take. Okay. So let us try to improve this differential. Still, this is not good enough. Exactly because of the persistent pole at infinity. So how can we do something better? So let us pick up 2 points, Z2 and say, sorry, Z3. And let them be marked points. Now, let us study zeros and poles of this differential as a function of Z1, Z2, and Z3. So it is a section of the cotangent bundle. And I'm looking for its zeros and poles. Naively, one might think that you have a pole here, or here, because of pole downstairs. However, Z1 and Z2 never collide on the moduli space. So actually it has no poles. Now, it's interesting, what about zeros? Clearly, there is a zero, there would be a zero when Z2 and Z3 would coincide. But what this would mean, Z2 and Z3 coincide, since they do not coincide. Actually, Z2 and Z3 coinciding means that they go in Deligne-Mumford compactification to another component. So this is configuration where we have 0 of the section. So actually, from the point of view of the first half, where we have Z1, Z2 and Z3 look as sitting here at the same point there where we have a junction of two components. Okay. Now, what may happen with the rest of the points? They could be or should be distributed between these two components. In particular, if n equals 4, we need to draw the 0 as follows. So n equal 4. So here we have Z1, Z4. So there is a 0 here. Z2, Z3. Plus possible configuration Z1, Z4, Z3, Z2. However, this configuration is not stable. So we could ignore it and say that psi at Z1 and let us say 1 at Z2. So let us consider a case where the only observable is 1. 1 at Z3, 1 at Z4, is a contribution of 1 at Z1, 1 at Z4, say O here, O dual observable, so it corresponds to factorization here. 1 at Z3, 1 at Z2. So in the simplest case, here we also have 1 So in the simplest case, here we have 1, and here we have 1. So this is, and we assume that correlator of 3 1s is 1. Assume. So we will get the answer that equals to 1.
I'm sorry, may I ask a question?
Yes.
So now here you already introduced the psi class, so or the
Yes.
psi, and the psi was our one form before.
Psi was not one form. Psi was the locus of the zeros
Ah, okay. Okay, I see.
of the one form.
Thank you.
It should be a differential form or cycle, depending on how would you treat it
Mhm.
on the moduli space.
Okay, thank you.
As you know, so definition was that it is the first Chern class of the line bundle
Mhm.
and associated to the point one. And you can consider any section you like. So we picked up very particular section. Let us make one more test here and as Pavel said, we need to have more examples. So if you are never doing this, let us consider the case where we have 5 points.
Mhm.
So now we have M not 5. So this has complex dimension 2. So we need 2 psi classes. So there are 2 cases. First case, psi square at Z1. And still 1. I'll write it like this. I will omit this standard Z2, Z3, Z4, Z5. So I assume it. So this is over M05. So it's case A. And there is also case B. Interesting. So let us do it case after case. So people were very surprised 30 years ago why they have to do such computations, I mean in physics. So first of all, how can we compute case B? We need to pick up some section here, and we already computed things with psi of Z2. So there are 2 cases. First case is, remember, we had to pick up 2 points. One approach is to pick up these 2 points. Let us call it B1. So for point Z1. Or we can pick up these 2 points. So let us first do case B1. and then compare it with B2. Case B1 means that we have to put these 2 points away, 1, 1, and there will be 1 on the neck. Here I'll have 1 on the opposite side of the neck, this 1 that is left. So I should have 5 points, yes? And psi is E2. Let me see. One, two, three. 1, 2, 3, 4, 5. And this one. Something is wrong in my computation. And of course we have 1 here at point Z1. So here I had 5 points. So here I should get 7 points. 1, 2, 3, 4, 5, 6, 7. That's why I get 1 from here. 1 from here. So answer is 1. If I take points like this, I would like to put psi Z2 here. But here I have clearly 0. So now I'm doing case B2. So it means I need to consider a situation where I'm leaving 3 points plus the neck on the second half of the sphere. Then I have 1 and 1. So that's why B1 and B2 give the same. So Dong, we are doing exercises in psi classes.
Apologies for late. There was a meeting in my department, and
Oh, it's okay. It's okay.
So, by the way, are we evaluate the psi class on the moduli space of?
Yes. Yes, today we will discuss psi classes.
Okay.
And psi classes and related equations. And related phenomena, I would say. Okay, so that's, Donald, is it clear how to make this computation?
Yes. Yes.
So are we equate the second and the third line?
So there are 2 ways to compute this thing. There was approach B1 that says that we considered the preferred. So we have to pick up 2 points. In case B1, we consider these 2 points. And in the approach B2, we took these 2 points. In each of these approaches, we get 1.
Okay.
Because you see, for people who never worked this, one has to have a warm up. It was too easy, too simple here. Now let us try to work out psi square. Here we also have two approaches, you see? We need to take, now we need, okay, we can take one. We can take only one section. So we need to pick up two points, say these two. Now, interesting thing happens. Know that these 2 points are different. So let me label these points: Z2, Z3, Z4, Z5. Still, I don't have enough size to get interesting to get interesting numbers. Still, I leave the Z4, Z5 outside, and I get psi Z1, 1 at Z2, 1 at Z3, and 1 as a double point. And here I have 1, 1, 1. So it's too simple. Actually, something more interesting would happen. I'm trying to say that there is a possibility to get more interesting numbers. So maybe it comes when you have 6 points. And you have psi at Z6. Because now, when you degenerate, you will have, say, here and here. You take Z5, Z6 as 1 and psi at Z6. Now you can put here either this or this or this. Now you have a room. And 1 would come out of this. 1, 2, 3, 4 points. And here you'll have psi square, sorry, psi together with 1, 2. points, yes. Because another one would come from the double point. So here you start to have some combinatorics. How these points are distributed among these two spheres. And in this particular case, coefficient is 3. So let me see. There should be a case where coefficient is 2. But let me see how can I get it. So here the answer seems to be 3. Because these 3 points should be distributed between these two components, such that 2 points come here and 1 point come here. So here the answer is 3. So maybe I computed psi square. No. Okay. And you can play on and on. You can undress psi step by step. Now, let me do another thing. So this thing was called gravity. So actually you'll find that answer could be written in terms of some factorials. So it's combinatorics. So I'm not going to compute the exact answer in all particular cases. Now let us consider so-called gravity coupled to matter. So to make life interesting, I'll do it in a non-standard way, in the way that we introduced with Kontsevich and Manin. Namely, we consider M0n with Deligne-Mumford compactification. However, n of 1 points were considered as inputs and 1 point considered as output. So cohomological field theory that we called oriented was the following. It associated to the vector space So there was a vector space, and the main object was a map v to the power n minus 1 to v tensor cohomology of M0n Deligne-Mumford. Now, let us consider the generations. So this is an output. We consider this point being an output for the sphere number 1 and input for the sphere number 2. So I was this, so main object, or I belong to V star to the tensor power n minus 1 tensor V tensor cohomology of M0n Deligne-Mumford. Actually, these were closed cycles. We consider actually factorizable cocycles. So factorizable cocycles mean whenever we have such configuration, so there is the moduli space of such configurations. And suppose that we have, and clearly this moduli space is a product, okay, I'll draw it in some detail. So moduli space of configurations of this type is actually the moduli space of this times the moduli space of this. So I call this presumably 1 second, 1 second, with a point here, with a point here. Now, cycle belonging to this moduli space becomes a product of the cycle here and cycle here. It could be the full space, or it could be some subspace. So these are marked points. And factorizability says that in such situation, I corresponding to cycle C is a composition. When I say composition, I mean that here we have very specific input where this output is coming. You see, we have very special point. So when we decompose this nodal surface like this, we have a distinguished point on the first component and distinguished point on the second component. We associate output to the distinguished point on the first component and input in the distinguished point on the second component. And here it is composition along distinguished along the vector spaces associated to distinguished points. So we consider factorizable cocycles. At the moment, there are no psi classes here at all. One can write down from factorizability, one can write down the equation for evaluation of I over the fundamental cycles, namely over the moduli space. And these equations turned out to be, we discussed it, I just recall, so-called oriented associativity equations. It's important to say that there is no need to have any kind of metric here. Just no need. In order to write them down, we do the following. We consider I top. So I top belongs to this space. Top cohomology. So it's a number. So we evaluate it here. So it's a number. So we have such objects. And they are assumed to be symmetric. Interchanges of inputs. So being symmetric under the interchanges of inputs, they may be considered as a Taylor coefficients of the formal vector field. Field on V.
Sorry, may I ask a maybe stupid question?
Yeah, sure, sure.
So we said we want this factorizability, right? And then we said that
Yes.
we will actually pick up a special point. Like if we factor, then the second factor has an output and a special input where we glue the output of the first factor into, right?
Yes.
And here now we say, okay, we want to be completely symmetric under these.
Yes.
So in this factorization, we basically,
Symmetric on over inputs.
okay, so the special input we put is like an extra,
So special point, it's an output.
yes. But in the factorization, I understood we need two special points, right? Like
Yes.
one special input as well. But this is actually something which comes extra.
From this is kind of the origin of the equation that I'll formulate right now. But first, I'd like to formulate equation,
Ah, okay.
and then I outline the then I'd like to outline the derivation.
Mhm.
So equation that comes out is the following. You see, if these are Taylor coefficients, I consider the vector field V of some coordinates t. It's a vector field because you see it takes values not in functions.
Mhm.
It takes value in the same space. So I may denote it like this, or just consider its component. Note that these coordinates t are very special. They are linear coordinates on V, of course. That vanish at 0. So the main statement would be that dVA over dTB dTc are structure constants of T of commutative and associative algebra. The fact that they are commutative, it's clear because partial derivatives commute. The fact that they are associative is less trivial. So this condition, TD, DTE, so what can I interchange? B and D. So this should be called associativity equation. And what is called associativity equation should be called cyclic associativity in regular terms. However, somehow nobody guessed this construction. Therefore, we had to invent another name for this, oriented.
Oh, the board is a bit cut off there.
Sorry?
The board is a bit cut off. The very first line is not entirely visible.
On the up, where it's cut
On the
off?
up, on the up, on top.
Okay.
Thank you.
So first, I'll explain the origin of this. And of course, the origin of this is that M04 is connected That's why such point where points 1 and 2 come together and 3 is away on M04 is equivalent in homology, in zeroth homology, to the case where 2 and 3 come together, and here is 1, here is output. So these two pictures represent two different points on M04. So this is the beginning. And then we can put the input. You see here we have inputs 1, 2, 3, 1, 2, 3. And then we can put an input number 4. So here we have statements that the quadratic term in vector fields satisfy some relations. So now we can put input number 4 here. And here we are just putting one more point. So it's on M05. And this sum is homological to putting 4 here plus putting 4 here. So it is a 4-term relation. It corresponds operation. It connects operation from 2 to 1 and 3 to 1. And it's exactly what is written in this oriented associativity equation. And then you can add more and more points. So this is situation without descendants, without psi classes. However, one may add psi classes here. So now we are combining things. Suppose we have M0. So for M03, it's too simple. Consider M04. Once again, Deligne-Mumford. We can have psi class associated to point Z1. Let us, for simplicity, consider psi classes only for inputs. Then we can compute the corresponding correlator. I would write it like this. Psi V1 is the first vector. V2, V3. So this is a vector. The result of operation is a vector associated to output. So now I'll write here output, just to keep in mind that there is an output point. Or maybe I will not write it like this. I just remember that now the correlator is a vector corresponding to the output. So actually this picture corresponds to 4 marked points. 1 point is an output. Now, similarly, I can take section of the standard form dz1 z1 minus z2 minus dz1 z1 minus z3, and then I'll have v1 and v2 and v3 going away. So here I have configuration like this. So I'm writing it as V2, V3 plugged in. So this I have to put as a first argument of this sphere where I have V1, and this is an output. But I may ask myself, what would happen if I put here not the point number 3, but Z of output? It would mean so V2 and output. It would mean that I will have the following decomposition. Here is the output. Here is the point Z2. I will write it as V2 at Z2. And here I'll have what is left, what was left. V1 and V3. So I can write it down as V1, V3, and here I have V2. But they should be the same. And of course, it means that first you multiply 1, 3, and then 2, and here you 2, 3, and then 1. Equality here is, of course, associativity. So it's interesting that you can get associativity not from the connectedness of M not 4. You can get it also from different choices of psi classes. So that's how it goes. Now, let me consider an important remark that physicists observed at the very beginning when they started to do all this stuff. Consider solution to oriented associativity. Note that we have equation like this. Such that this is associative, and we just don't care about what happens where we have constant terms here, linear and linear term in T. Note that we can make the following, so that from this equation we can get a new equation just by making shift. Let me see how to call this shift. I'll call it TB. Here B stands for what? B stands for background. So this would be a new solution. So equation is invariant under under constant shifts. So what would it mean? So what does it mean? It means that if we have an operation I, set of operations, we can go to the new set of operations. For fixed T here. So how do we understand this? This shift. We understand it. So if we imagine that it comes from quantum field theory, we understand it as a change of the Lagrangian, because we put something on these points and we integrate. So it's a change of the action. So we call it new background. And in some particular example, people managed to identify these shifted backgrounds. I will not go into details on this. What is interesting is that you can use in the shift of the background not only V itself, but also cases where you have psi classes. So psi classes could be also considered as shifts of the background. So one has to work it out somehow. It is not obvious, because observables corresponding to psi classes were defined in a very different way. In particular, they did not take part in this factorization. So it is kind of a claim. So it means somehow that the space V conjecturally could be extended to the loop space. Note that in this presentation of this phenomena, now I appeal to people who heard about it before. There is no such a notion as neither you have metric nor identity. In this formalism, you just do not need it. So I haven't checked this for a while. Maybe it will be a good exercise to see if I'm telling you the truth, the truth. Okay. Okay, maybe so. Let us make another exercise. Let us try to check it, if it's true or not. So what would be the easiest way to check it? Let us consider simplest case. Oh, no. If it will be too simple, we will not be able to check it. Because simplest case is when v of t is just quadratic. In this case, I have no room to deform. I'm sorry, it would not be interesting. So suppose we have VA of t, that is FABC TBTC plus FABCD TBTC-TD. So such situation is possible. And of course, we impose these conditions. So here I should divide by 2, and here. So there are nice normalizations. I think that here I have to divide by 3 factorial. So let us first do the standard shift. T plus T background. Then we will get, of course, linear and constant term. But linear and constant term do not enter the equation. So if T goes to T background, FABC gets FABCD T background D. So I think that if we check associativity equation here, for the new f a b c new, so associativity here brings some quadratic relation here. So this would go however, there'll be a much more trickier case when we will do the following. When we will change things due to the psi class observable. Maybe we should work out this example, because this is not that trivial. So now, new operation 1, 2 to output is modified by putting here some V naught times psi class. So the new operation f tilde ABC would be an old FABC plus, what should we have here? V naught 1, V1, V2, V naught V1, then we have V2, and then we go out. So I'll write it like this. FBCE FE. Okay, and here I put not A. So is it obvious that this is so this is commutative, but is it obvious that it is associative? Okay, and of course I put here epsilon. So we need to consider it in the first order in epsilon. So what would you say?
Here V0 is fixed.
Yes, it's fixed.
Element. And I don't think it's associative, right?
Interesting. Well, let us see. In the first order in epsilon.
A first order.
First order in epsilon. Hmm?
Then it is.
How do you know it so fast?
At first, if epsilon is not the first order, I will put more and more psi to make it associative.
Of course,
And then-
but yes, but why it is associative as a first order?
I'm not sure in that way. I would love to hear the explanations.
Oh, okay. So I think it's a matter of computation, right? Mm. Mm. So before we will make computation, let us make a check. The simplest check is, suppose that f is semi-simple. So before let us, how to say it, we call it tries. We try. So no, tries are written not this way. Experiments. If f is semi-simple, so it means that f ABC is delta BC delta AC, no summation. In this case, it's absolutely clear that it is still associative, and in this case for any epsilon. But it was the first try. However, what if f is not semi-simple? So let me make another experiment. What is the simplest case of something non-semi-simple? You multiply polynomials and you divide by some relation. Suppose polynomials are of one variable. So say this 3-point function is the simplest way to see something commutative associative where contour rounds around somewhere in the x-plane. So for some simple case, this f is a product of monomial with different roots. Just imagine that roots are the same. Okay? So this new multiplication table somehow means that we put another p tilde in this multiplication table. And of course, everything is still associative. Associativity is preserved. So, actually, I am putting here 1 plus epsilon p tilde. This is still associative. So my statement is that this is still associative multiplication. So let me comment on this. When I write things this way, exactly this way, I assume that I have polynomial and some Frobenius structure, namely some linear function. So if you don't like f of x, you may put here any one form. But you can put this one form into this f of x downstairs. Now, the deformation like this still brings associative multiplication, because this 1 plus epsilon p of x somehow renormalizes the function f of x downstairs. So it is kind of exercise. However, I still think that we can prove it explicitly. One, two, three output. Equals one, two, three output. Now we are making the deformation. We are making it here and here. and also here and here. So now 1, 2 output. So deformation is we put here something 0 plus we are putting here something. So we are deforming here and here. So from commutativity and associativity of multiplication, it is clear that these two terms equal to each other. So here is just a product of 0, 1, 2, 3. And here is again a product of 0, 1, 2, 3. Twice. The same here. So they actually are equal to each other. While it's not that obvious from the very beginning. So once again, it was an exercise for an exercise, right? Because here we studied only first descendant, and we considered only the lowest term, namely associativity. The proper thing to check or to prove would be higher quadratic relations. And not only to the first order, not only due to the first descendant, but also to higher descendants. So it's interesting, but it works. And this fact is known as, so physicists use their own slang. When they first discovered it, they called it big phase space. They discovered it immediately. So it's quite interesting that so-called gravitational descendants of psi classes may be considered as a change of the theory. Now, that's what happens with the oriented associativity equations. In what follows, it seems that it is useful to study another version of this story. And this is the same thing on LM spaces that are even simpler. However, such story on LM spaces, and here so unfortunately we did not study it with Manin, but it was done by Shadrin and Zvonkin. You consider such space. So here we have, of course, at least one point. So these are LM spaces. These points could collide. Still, we have 2 points. Special input, special output. So basically, LM points is the C star to the power n over C star compactified. So this is 0, this is infinity. So this may be closely related to equivariant volume story. And everything is the same. And we have maps, I would say. U to the power n times endomorphisms of V. So here is V, and here is U space. These black points do not coincide with white points. However, they could coincide with each other. So the main object I lives here and in, of course, cohomology of the LM space. So we studied this when we studied commutativity equation. Now, I want to mention that it's possible to study psi classes as the input and psi classes as the output. This space is different from the Deligne-Mumford space. Still, psi classes are doable. So here we have a global coordinate. So we can write down differential at 0. And the best differential would be something like this. So this corresponds to taking the first point output. And here the I is one of the points standing here. So argument would be similar. The zeros go to configuration where point I is at infinity. Maybe I wrote it in the wrong way. Here it seems that it's at 0 minus the infinity. So I'm writing down one form here, and I have 2 points. One is point infinity, one is some of the points here, and since they do not come to 0, we have null poles. So argument is exactly the same. So 0 is when these points bubbles out, goes together to infinity. So we can define correlator where the incoming something has psi classes and the outgoing something also has psi classes. So how should we write it? So it goes from the right to the left. So main object E of U psi V. I need to pick up several U's. U1, UN. So here is a psi class. And I need to pick up very fixed point I. It's E with a lot of U. V. And E here we have UI. And also a lot of U. And composition. So it's possible to get psi. And also higher powers of psi. So now let us see what happens if you add, if you consider one U, two U's, many U's. You will get the following. Consider this as a function on the U space with linear coordinates t small. Remember that we had A of t. So it's an operator from V to V whose Taylor coefficients in t were these operations. So such condition would actually mean so how to write it down? So here we have UI, and here we have UI, and here we do not have this UI. So this is a new object. I will call it A psi V. So it means that there is psi here. Equals to what? A original over DTI. And here A. Now, let us consider the following generating function, A of Z that is sum over n, A psi to the power n, and it turns out that it's convenient to divide it by Z to the power n plus 1. Then it turns out that such AZ is a solution to equation dAZ equals 1 over Z dA A of Z. So it means that such A of Z is the so-called Baker function or eigenfunction of the integrable system D minus 1 over Z dA that we studied above. And it is very instructive to compare this A of Z with the equivariant volumes. So here I have some problems. It should be true, but I have not finished the correspondence. So if this is true, so conjecture, A of Z should be related to equivariant volumes. And if this is true, it would tie theory of equivariant volumes as a particular example to the theory of configuration space and moduli spaces. And I hope that tomorrow we will try to find if there is such a relation or not. So in this way, it would be so-called Giventhal theory. Okay, so it would be a conjectural Giventhal theory. So it would mean that would this be true? Just imagine that this is true. Imagine that this is true. Then it would be very instructive to find the higher dimensional analogs of this. And of course, there will be not only one Z, there will be several Z's. And would it be true? Equivariant volume story would serve just as a representation of a more general theory. So it's somehow a reason why it's important to study equivariant. It's one of the reasons why it's important to study equivariant volumes. So here I have some problems in understanding. I hope that I will clear them by tomorrow. But if I will not clear them up by tomorrow, I'll share with you my troubles. Okay? So that's what I want. In particular, I would like to understand the analog of psi classes in complex dimension 2. These psi classes should be related to formulas like this, to equivariant volumes like this. Okay, that's it for today.
Yeah, thank you very much. It was very interesting.
Thank you.
So I would recommend you to make this exercise.
So, so at the first part of the lecture, you do psi class calculations on a Deligne-Mumford compactification.
Yes, because they are more standard.
Yes, they are standard.
And I also mentioned interesting phenomena.
Yes,
It's called the phenomena of the big phase space.
Can I consider it as a string equation in the literature?
So string equation. So people call it differently. It's called the big R. Yes. So people call different things string equation, but in some sense, yes.
Okay.
So similar equation was called string equation. However, the equation was the interpretation. So people mostly were talking about in topological gravity. They were talking about dependence on the 2-point function on higher times. They considered 2-point function that depended on higher times of k-peak hierarchy.
And you're saying this connection equation in the board that looks like the equation looks like the connection thing is the counterpart for Losseff-Manin's phase.
This is not exactly, because so these are two different things.
A different thing.
So yes. So when there were higher times, it was an evolution of the system along the higher times.
Okay. Yeah.
So I could not speak about it, not explaining that. So actually, my today's talk consisted of two parts. First part is also very intriguing because of what? Because if you consider the type B model, okay, I'll say something about it. When you consider type B model, you should consider not only one very distinguished holomorphic top form, but you should consider perturbatively all of them. So you have a lot of choices. It is hard to see these choices in Calabi-Yau setup, but you may see them in the following way. So we know that okay, let me comment on this. So let me say what I think about the big phase space for Calabi-Yau. First case A, Landau-Ginzburg model. All top forms, almost, are okay. So theory depends not only on the singularity, but also on the top form. So you may consider this as a starting top form, but you may as well consider polynomial with the only condition that if you put in polyvectors, you generate everything. Say all differential forms. So how could it be? So in Landau-Ginzburg case, it's very easy. You just need this form to be equivalent to dx1, dxn, maybe with some constant, in d bar plus dw, okay, cohomology. Okay, so no d bar in dw cohomology. So it means that P of x should not have zeros in some particular places. Or, perturbatively, you can consider form as dx1, dxn plus with infinitesimal coefficients, epsilon alpha, any polynomial infinitesimal means that you factorize by ideal like this, or you consider this epsilon formal. You can take anything of this. And it would be okay. Now, if you consider compact Calabi-Yau case, also possible. So you consider holomorphic top form plus with infinitesimal coefficients any other forms, PQ. With the only condition that they should be d bar closed. So if epsilon alpha are formal, this is also primitive. So here there is some, let me put some quotation marks. Here I'm not 100% sure, but such theory in complex dimension 1 was developed. On Riemann surface without the set of points. By Krichever in 92. So he considered sigma with superpotential, and he considered holomorphic form here of a very general type. And he considers big phase space making evolution of this form. So I and the Polyubin studied the particular case of AN. But in general, you may study this. So this is, and in different complex dimension. So this is what I think the big phase space is. So since we are not talking about the B model in detail, yes? Because it will be hard to sell it nowadays. Still, it's possible to sell it. So it is another thing where psi classes are important. And this is the meaning of the big phase space.
Okay, thank you.
Okay. So there actually is a theory, not only formal answers. So what I explained you today, or started to explain, that if you have a theory, you can formally deform it along observables containing psi classes, but you probably don't know what geometrically happens. You see, it's like having, so when you deform an answer, it's like studying cohomology without having the manifold or something whose cohomology you consider. And there is a model, there is a way, okay, the geometry from which this cohomology could be computed. Okay.
Thank you. Then
Thanks
see you
a lot.
tomorrow. Thank you. Thank you
See you
for the lecture.
tomorrow.
Okay. See you tomorrow. Thanks.